Now that we've learned the naming system for oxyacids, it's time to look at the synthesis reactions that lead to the production of oxyacids and the environmental consequences that can result when these reactions occur more than they naturally should. So when we say synthesis reactions, we are actually being literal with these reactions in that if we look at these reactions here, we can see that they follow the same basic outline of a synthesis reaction where we have two smaller reactants, which we will call A and B, that join together in order to produce a larger product compound, which we will simply call AB. The only difference in oxyacid synthesis reactions is that the A and B are actually compounds rather than individual elements such as the elements that we see that produce binary acids, but we can see that pretty much all acids can be produced through a series of relatively simple synthesis reactions. Now, the A and B pattern is actually very easy to establish here. For example, we can see that the B in all of these reactions is going to be water, and this kind of explains where some of the oxygen comes from because, again, these are oxyacids. But the actual A compound in all of these cases is what we call a non-metal oxide, which is simply a compound that contains oxygen where the other element in the compound is basically any non-metal. For example, the most widely known non-metal oxide is actually carbon dioxide, which is indeed the same gas that every animal exhales as a waste product of our energy production process. And when carbon dioxide reacts with water, it produces this acid, carbonic acid, as we see here. And we'll talk about what the environmental consequences can be of having carbonic acid levels that are extraordinarily high. But if we weren't familiar with a non-metal oxide such as carbon dioxide, we can actually figure out which non-metal oxide is required in order to produce all of these acids here simply by taking the acid formula, for example H2SO3, sulfurous acid, and removing water from that formula. So if we remove the H2 and one of the O's, the non-metal oxide that we would have left would be sulfur dioxide, which is actually a very common pollutant gas, and we'll talk about what the sources of this potential pollutant gas are. Likewise, if we remove H2O from sulfuric acid that we see here, remove 2 hydrogens and 1 oxygen, and we end up with a different but similar non-metal oxide gas, sulfur trioxide here. Finally, if we ignore my totally unintentional mistake here and write the formula for silicic acid, H2SiO3, as it was written here, if we remove water from the chemical formula of silicic acid, we end up with silicon dioxide, which again is technically a non-metal oxide, but silicon dioxide is actually solid at room temperature, meaning that this reaction occurs relatively slowly, and that kind of makes sense because silicon dioxide is actually the chemical formula for both sand and the heated and pressurized form of sand, which of course is window glass. And obviously people are used to their windows actually being able to withstand rain that falls and not turn into the acid form here. This reaction technically does occur, but very, very, very slowly, and water will take decades, if not centuries, in order to completely react with all of the glass within your windows and produce this acid here. And as it turns out, the non-metal oxides that we are primarily interested in terms of looking at environmental consequences, are the ones that exist in gas form. Because if we can answer where these gases come from, we can answer where most of the oxyacids that exist in nature come from as well. Now, some of the sources of non-metal oxide gases are actually perfectly natural. For example, the bottom image, we can see a volcanic eruption here, and some of the most common gases that are released in addition to carbon dioxide are sulfur oxides, such as sulfur dioxide here, as well as nitrogen oxides, such as nitrogen dioxide here, and all of these compounds can react with the water vapor that exists in the atmosphere here. Remember that clouds are basically entirely made of water in its gas form, but we'll talk about what the ramifications of this are subsequently. Now, there are obviously non-natural sources of non-metal oxide pollution. For example, the image above showing industrial pollution that we see very, very regularly, both from industrial production and simply from transportation. Remember that every time your car burns gasoline, it is releasing large amounts of carbon dioxide into the atmosphere, and if you're using fuel that hasn't been properly refined, it would have a lot of non-organic contaminants in the form of sulfur compounds and nitrogen compounds as well. However, by far, as mentioned previously, the most common non-metal oxide is actually carbon dioxide, because it comes from pretty much every organism on Earth that requires cellular respiration as a source of energy. So animals, including us, require a way to get rid of our carbon dioxide, because we produce this as a waste product of cellular respiration, which is our chemical reaction to produce energy. So of course we exhale it, and that carbon dioxide eventually is going to end up in the atmosphere along with all of the other non-metal oxides that have been released either from natural or artificial processes here. Though the problem, as we'll see, occurs when those non-metal oxides make it to clouds, because if we use carbon dioxide as an example, the carbon dioxide can react with the water vapor in the clouds in order to produce, in this case, carbonic acid, but this technically can happen with nitrogen oxides and sulfur oxides as well. Now, when these acids are produced, they're not just going to stay in the clouds forever. They're going to fall back to Earth whenever the water turns from a gas into a liquid. In other words, whenever precipitation occurs, whether it be rain or snow. And if the acid that forms in the clouds falls back to Earth with the rest of this water, we have the technical term for which being called acidic precipitation, although most people would colloquially refer to this simply as acid rain. Now, there are a lot of misunderstandings about acid rain, about how it's dangerous for people. The reality is, however sad it may be, that most of the rain that hits you, if you live in an industrialized city that has large amounts of industrial production or fossil fuel burning cars, most of the rain that hits you is going to have an acidic pH, but obviously it's not strong enough an acid to melt us or burn us the way that stomach acid would. Instead, the major danger caused by acid rain is the danger that it poses to soil and to the plant life that depends on soil. Because whenever it rains, that rainwater is going to pass through the ground and naturally dissolve a lot of the nutrients that exist within the soil. This is how nutrients are transported from one location to another location with the assistance of the rain. This is a natural process. The problem is that acid being present in the rain is not only going to dissolve more nutrients within the soil, but it's also going to dissolve a lot of the nutrients that are in the plant life growing in that soil as well. And when that rain falls and that acid dissolves all of these nutrients, it's going to take a lot of those nutrients with it as the water drains through the soil, removing those nutrients to be available for plants to be able to grow. And this process is what we call nutrient leaching. And this can absolutely devastate whole ecosystems, because if these nutrients are drained by the acid rain out of the soil, Now that soil no longer has enough nutrients to support the growth of large plants, particularly trees, resulting in them dying, as we can see in this forest that has been devastated by acid rain. Now, if you remove the bottom of a food chain, i.e. the producers, you are also going to affect all of the organisms that depend on trees for their food source and also for their source of shelter, and this is the true consequence of acid rain that has much more devastating effects environmentally than it does to individual humans that are subjected to acid rain. In our final video, now that we've finished looking at where acids come from, our final video in this series is going to look at the synthesis reactions that produce the bases that exist in nature, so that we have a complete picture about where most acids and bases originate from.